Okay, so this is going to be an explanation of the AP problem on page 82, but before we start going through that problem, let's kind of review something from just talking about series in general. So let's say I give you a series, 1 plus x squared plus x cubed, etc. So plus dot dot dot, so that represents some function, and based on that function, I recognize that that is a geometric series. Your a is 1, your r is x, so I can write that entire series as the sum is 1 over 1 minus x. So this is the function. So the function is equal to this entire infinite series, which is also equal to the sum of that series, which is 1 over 1 minus x. So this represents this entire series. So now, based on that, if I asked you to evaluate f of 1/2, it would be the same as plugging in 1/2 in for x. So you could do that. And then the sum of that infinite series would be, again, if you look at this, it's your geometric. It's a over 1 minus r. Or we already have the sum here. It's the same as plugging in 1/2 into x here. Because again, this series is the same as this function. Now, let's say I ask you to take the derivative of this. If I ask you to take this derivative and I ask you to come up with the first couple terms, we would just go through and come up with the derivative of this term, which is 0. The derivative of this gives me 1. The derivative of this gives me my 2x. The derivative of this gives me my 3x squared. The derivative of this gives me my 4x cubed. Now, if I want to come up with a way to represent this infinite series as a function, basically we can take the derivative of the function notation up here. The idea is this: you have this big equation here. This entire series is equal to this function. What I'm asking you to do is perform an operation on this. I'm asking you to take the derivative of all of these terms. So anything I do to one side, I need you to do the right side. So the derivative of this are these terms. I can also take the derivative of this. I'm going to rewrite that as 1 minus x to the negative 1. So that's f. So f prime would be negative 1, 1 minus x to the negative 2. Do your chain rule. There's my f prime. So this entire series added up is really the same as 1 over 1 minus x squared. And there's no way we could come up with this because this is not a geometric series anymore. But using the idea I knew what the original function was, I can just go ahead and find the derivative using this original function. So then if I ask you to find f prime of 1/2, I could go ahead and again plug in 1/2 for x everywhere. And since I also know the function notation, this would be the same as 1 minus 1/2 all squared, replacing that x with the 1/2. The idea is, even though this is no longer a geometric series, I can still find the function, which is the sum, by using this idea here. Because if I take the derivative of this side and take the derivative of this side, these two p's should still be equal. Okay, so now let's take a look at what was on page 82. Okay, so part A is the straightforward piece. So they're asking for the first 3 non-zero terms. So I'm going to just use this. And let's take the first couple derivatives. So the derivative of the first term is just 0. The next one is negative 3x squared. Then the next term is 6x to the 5th. The next one is negative 9x to the 8th. There's my 3 non-zero terms, plus dot dot dot. And then remember we talked about, instead of trying to figure out what this pattern is, I'm going to use for the rule for taking a derivative from the general term. So my general term would be negative 1 to the n, bring down the 3n, reduce the power by 1. There's my general term, put it in the middle, put a plus dot dot dot. Now it is saying, can you use what you got from part A to find the sum of this infinite series? So notice it is asking for a sum, but if I look at this series, it is not a geometric series anymore. The bottom you are multiplying by 2 to the 3rd, but the top you are not multiplying by the same number every time. You are actually adding 3 every time. But the connection is, oh, doesn't this look very similar to this? But instead of having an x, what number had they plugged in for x? This is really f prime of 1/2. So when you plug in the 1/2 for x, that's why the 2 squared is on the bottom. When I plug in the 1/2 here, it's really There's my 6 that matches up. There's my 1/2 to the 5th, etc. So when you look at your general term, they've simplified it a little bit, but there's my 3 to the n, there's my 1/2 on the bottom. So the x is really the same as 1/2. So the idea is, how am I going to come up with the sum? Well, we knew, they told us that this entire series is 1 over 1 plus x cubed. So this is an equation right here. I took the derivative of this side to get the first couple terms. I can take the derivative of this to get what this entire series is equal to. So if you take the derivative, again, I rewrote it as 1 plus x cubed to the -1. So I brought down the -1, reduced the power by 1, do the chain rule. So this is this function. So this entire series is really adds up to this. So what do they want you to do for x? They want you to plug in 1/2 for x. So when you plug in x equals 1/2 there, that's how I get to my answer. I did simplify it to be -16 over 27. Okay. Part C. Okay. Part C is asking you to come up with the first 4 non-zero terms for this function. So I am going to take what I got in the original, and so which is up here, and they want it in terms of t. So I'm going to take the first 4 terms in terms of t. Oops, minus t to the 9th, and I'm going to integrate it. And my first term is t minus t to the 4th over 4 plus t to the 7th over 7 minus t to the 10th over 10, and I know it goes on. And I need to plug in 0 and x, so all that happens is the t becomes an x. So this is my answer. And I know when I plug in 0, all the rest of the terms will be zeroed out. Here are my first 4 terms, dot, 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 and I am integrating the original function f. So I'm going to go back to the original and take the antiderivative using the general term. So add 1, divide by the power, there's my general term, plus dot, dot, dot. Okay? Lastly, part D. It says use the first 3 non-zero terms found in part C. So here are my first 3 terms in part C to approximate this antiderivative. So I'm going to integrate x minus x to the 4th. So this is my antiderivative, sorry. So I already integrated it from part C. They want you to tell them what happens from 0 to 1/2. I'm going to plug in my bounds, 1/2 minus 1/2 to the 4th over 4 plus 1/2 to the 7th over 7. So there's my first 3 terms. You can leave your answer like this. Okay. Now the next part of this question says, what are the properties of the series representing this that guarantee that this approximation is within 1/10,000 of the exact original value? So basically they're saying, what this question is asking, how do you know that the error is less than 1 over 10,000? So basically they're giving you the maximum error. How do you know that the exact error is less than that? Well, here's the idea. I only use these 3 terms to do the approximation. So remember we talked about the error always comes from the next term over. So look back at part C. What's the next term that we cut off? X to the 10th over 10. And when we do error, we don't care about positive or negative. We always do absolute value. And what number have I plugged in for x? It's just 1/2. So this is your error. And if you punch this in your calculator, you will notice that this is less than 1 over 10,000. This one, I do not have to there's nothing about maximizing the derivative because this happens to be an alternating series that converges. So those are the conditions, those are the properties. So all I have to do is pick out the next term, and that's it. That is your error.